Welcome back to part 2 of solving hard trigonometry questions using identities. Today we're going to look at actually using the identities to simplify the equations to get them into forms that we had from our previous part 1 session, either the quadratic trigonometric forms or factorizable trigonometric forms. To do this, we're going to need to make sure we have good knowledge of the identities that we are going to be using to help us. The first identity is one we have used many times in trig solving so far, and that is that sine of a specific angle, let's say theta, divided by cos of the same angle is always the same as tan of that same angle. The angles do not cancel in this type of situation. The angle should be consistent in all three parts. The second primary identity is that the square of sine theta plus the square of cos theta is always equal to 1. We don't tend to use this identity in this form exactly, but by rearranging we can get something along the lines of the fact that sine squared theta is equal to 1 minus cos squared theta, and likewise that cos squared theta is equal to 1 minus sine squared theta. These forms tend to be very useful for substituting out troublesome trigonometric terms that are in the way of us solving our equations. So in equations that are going to involve multiple types of trigonometric form, i.e. some cos and some sine, we can use these identities to convert these questions so that they only contain cos or sine, but not both. Let's look at the example 4 cos squared theta minus 5 sine theta minus 5 equals 0. This equation clearly has a mixture of cos thetas and sine thetas, and we're going to use the identities in order to convert. Now, you always want to convert the terms that are easiest to substitute using your identities, and because our identities are always involving squared amounts, we definitely want to be converting the cos squared into sines, not the sine into coses. If we are doing so using the identity that I've got in the bottom right hand corner, we can replace the cos squared with 1 minus sine squared. These are obviously equivalent statements, so there's no difference being made to the size of the part of the equation or expression, but what it does allow us to do is to then complete the technique from last video where we substitute out sine theta for another variable, let's say y or w in my preferred case, and that will allow us to write the equation as a fake quadratic. So if we allow sine theta to be our substituted value, let's say w, then we have 4 1 minus w squared take away 5w minus 5. And this quadratic-like form is something we should be able to solve without issue in order to make sine theta the subject of several equations. Expanding the brackets gives us 4 minus 4w squared minus 5w minus 5. Simplifying further gives 4w squared plus 5w plus 1 equals 0. We can then factorize this quadratic into 4w plus 1, w plus 1, and this gives us values for w of minus 1 and negative 1 over 4. In the same way as we did last week, we then are able to split this into two separate questions. Since w is equal to sine theta, we have sine theta equals minus 1, which we could solve without problem, and sine theta equals minus a quarter, which we could solve without problem. I'll leave you to complete the remaining of those tasks either using the ASTC diagram or a general solution style technique. But you can see how the identities would be useful in order to transform problems and questions involving multiple different types of trigonometric form into equations that have the same type of trigonometric form. Let's follow up with a second example involving the use of our other identity. Let's solve, and we'll do the full question this time, for theta between minus 180 and 180. And we'll solve 3 sine theta equals tan theta. So in this equation, we once again have a mixture of different trigonometric forms. We've got a sine and a tan, and we can't solve problems that involve sine and tan at the same time. So the best thing to do is to try and get things all in terms of sine or all in terms of tan separately. Now, unfortunately, there is no identity that directly takes sine thetas into tan thetas, but we can, by replacing the tan theta with something involving a sine theta, utilize factorization to our advantage. By replacing tan theta with sine theta over cos theta, using the identity above, we can then move everything to one side and factorize out a sine theta. Factorizing using single brackets is an uncommon but very useful tool in trigonometric equation solving. Don't always be looking for the two-factor factorization that we did in the previous question. Sometimes a single factor bracket can be just as effective. By removing sine theta from both terms, we are left with 3 minus 1 over cos theta inside the single bracket. And just in the same way that we can say in double bracket situations that each element can be equal to 0, we can do the same here. We don't even have to replace the cos for a sine or the sine for a cos, because we now know that either sine theta is equal to 0, which would be the result if the outside element was causing the 0 from the product, or 3 minus 1 over cos theta is equal to 0. And so we have still managed to separate into two separate equations, so they have an individual trigonometric amount in each equation. The solutions for sine theta equals 0 between 0 and 180, where those values are included, go back and edit that, are, of course, negative 180, 0, and 180. We don't really need any cast diagram or general solutions to assert that. We can just use our basic knowledge of the sine graph. The second equation, slightly more tricky. After some rearranging, we get that 1/3 is equal to cos theta. And in order to solve this, I'm going to use a general solutions method. So we do inverse cos of 1/3, giving us 70.5 as our primary value for theta. The secondary solution for cos is given by 360 minus the first or primary solution for cos. So 360 minus this answer is 289.5, or just 289 to 3 significant figures. And I then need to make sure I have all the solutions within my original range, which, as we can see from the beginning of the question, was between minus 180 and 180. Some of the solutions may well be before these two values that we've calculated, so I'm going to subtract 360 from both values in order to calculate their previous solutions. 70.5 minus 360 is minus 289, and 289 minus 360 is minus 70.5. Cos graph always gives nice symmetrical solutions, which is why there's no coincidence that these numbers are matched. But we can see now then that the 70.5 solution and the minus 70.5 solution are within our range of values for theta, but the negative 289 and positive 289 are not. This brings our total number of solutions in this equation to 5. So theta is equal to minus 180 minus 70.5, 0, 70.5, and 180. And utilizing this idea of identity substitution plus the ability to factorize even into a single bracket allows us to split up the equation into small and manageable chunks that we can then solve on an individual basis.